So let's look at integration by parts. First off, what is it? Integration by parts is a method to integrate by taking one derivative and one antiderivative. Why do we need it? So integration by parts is probably the third thing I would check for most general integrals. So first, we would try to take a direct antiderivative, like the antiderivative of cosine x is sine of x plus c dx. There. If that doesn't work, the second thing we would try is use substitution. So for instance, the antiderivative of x sine x squared is going to be, integral of x sine x squared dx is going to be negative 1/2 cosine x squared plus c. If use substitution doesn't work, then we will try integration by parts. And here's the important thing. Integration by parts is the counterpart of the product rule. Like use substitution was the counterpart of chain rule. So how do we do it? Well, what we end up doing is this. So the formula is this. The integral of u dv is equal to u times v minus the integral of v du. And we choose a u and choose a v. Let me do a different color for that. The u we're going to end up needing to take the derivative of. And the dv we're going to take the antiderivative of. And in here, for the u, a little trick is to follow L, I, P, E, T. This will generally work, where if I see a logarithm, I'll use that for the derivative part for u. If there's no logarithm, then I'll go to inverse trig. If there's no inverse trig function, I'll go to any polynomial. That includes power functions. If there's no polynomial, I'll go to exponential. And if there's no exponential, then I'll go to trig functions as my choice for u, and everything else would go into dv. I'm going to be showing 3 examples, the first one 2 different ways, but I'll have the time codes in the description down below, so if you want to skip over things, you can get there. The next thing we're going to do is write a quick proof for this. So if I wanted to prove that the integral of u dv will equal uv minus the integral of v du, what I'll do is this. First, recall that the derivative, and I'm going to write like this is just a d, but I can have d dx, but the derivative of u times v is going to be v times the derivative of u plus u times the derivative of v. That's product rule. And now I can take the antiderivative of both sides, and when I take the antiderivative of a sum, that's the same thing as the sum of the antiderivative, so I just do it twice here. By the first fundamental theorem of calculus, the antiderivative of the derivative will just be the inner function, u times v. And I could work in a plus c, but I'm going to show it doesn't actually matter here. So that's going to equal the integral of v du plus the integral of u dv. And if I just solve for u dv by subtracting this from both sides, I will get the integral of u dv will equal this uv minus the integral of v du. QED, that's what's to be shown. So in here I don't need the plus c really, and I could sort of put one in here. But since I still have both indefinite integrals here, there will be plus c's working out on both sides. I don't need to have an additional one. Okay, so that's a quick proof. Let's see how it's done. And there are really sort of three ways to do it. A direct way, a way with a table method that does multiple sides, and then the hardest case is where you get a cycle. Let's start off with the simple case. So, and this one shouldn't be again, sorry. We'll see it later again. I miscopied one of these. Evaluate this. So I need to choose u, and I'm going to follow that lipit. There are no logs, there are no inverse trig, there is a polynomial. That's going to be x. And then dv is going to be everything else, sine x dx. And I'll take the derivative here, and that'll get me to du equals dx. I'm going to take the antiderivative here, and that will get me v equals negative cosine x. And I don't need a plus c here. I'll work the plus c's in at the end. I could put it here, but we'll get that at the end, just sort of fill it in the end so we don't carry around too much junk. And so now I know this. The integral of u dv is going to equal u times v, so that's negative x cosine x, so I'll label it all at the end, minus the integral of v du, which is going to be negative cosine x dx. So in here we have this here is u, this here is u, this here is du, and this is dv, this is v, and this is v. So that's the formula. That's following through. The integral of u dv equals uv minus the integral of v du. And now I just finish it off. So I see that a minus and a minus, this is a constant, I can bring it out, and those will cancel out. And now, notice how in here I had this sort of product going on, but the nice thing about integration by parts is if I have this polynomial term or some other terms, they're going to sort of work their way out, and now I just have the antiderivative of cosine of x. So this term remains the same, negative x cosine x. The antiderivative of cosine x is sine x. And since I've taken all of the antiderivatives here, I will have a plus c. Now, sometimes, like in this case, I just had an x, I was able to get through it in one step. But what would happen if this didn't go away right away and I had to do it multiple times? That can be a big pain. So there's a nice table method. And the way the table method works is you basically choose u and dv, and then repeat the derivative and antiderivative until one cancels. So you're going to end up with a table u dv, and you're going to basically get stuff in each of these spots until one of them goes to 0. And then, after that, you take alternating positive and negative products. And here's the idea. So I'll take the first term from this and the second term from that, and that will be positive. That's the uv. And then I'll take the second term and third term, that one's going to be negative, and that's going to be, that's from the minus integral of v du. And it just alternates because in our formula we have that minus sign that's going to alternate the signs every single time. And when we get this 0 over here, 0 times anything is 0, so that's going to kick us out, and we'll be done. Let's see this one again using the table method. So I will choose u. I will choose dv. U is x, dv is sine x. And this way I take the derivative. So on this side I'm taking the derivative. And on this side I'm taking the antiderivative. So derivative of x is 1, derivative of 1 is 0. Antiderivative of sine x is negative cosine x. Antiderivative of negative cosine x is negative sine x. And then I just take these diagonals. So this one to this one, this one to this one, this will be positive, this one will be negative. And so I get a positive x times negative cosine x, which is negative x cosine x. And I take a negative 1 times negative sine x, which is going to be a positive sine x plus c. And that's the answer there. Same thing we got from that slide earlier, but much easier to notate. And it can be used for much more annoying problems. So look at this. Evaluate the definite integral, so not a plus c at the end here, of this. And I can do it the same way. So I will choose u, I will choose dv. Following the rules for u, no logs, no inverse trig, but I have a polynomial, so I'm going to use x cubed as u, and I'll have everything else as dv. And I'm not going to write the dx here, I'll just make sure to wrap it up nicely. We take derivatives here, so on this, derivative of x cubed is 3x squared, derivative of that is 6x, derivative of 6x is 6, derivative of 6 is 0. And that's the important thing, this term goes to 0, while this one doesn't blow up to being more difficult. So we take antiderivatives here. The antiderivative of e to the 3x is 1/3 e to the 3x. The antiderivative of that is 1/9 e to the 3x. The antiderivative of that is 1/27 e to the 3x, and the antiderivative of that is 1/81 e to the 3x. And now I take my products with a positive, negative, positive, negative. That's not a negative sign, that's a negative sign. And so I will get from this x cubed times 1/3 e to the 3x, so that's x cubed e to the 3x over 3 minus 3x squared times 1/9 e to the 3x. Well, the 3 and the 1/9 give me a 1/3. And I have x squared e to the 3x. And then I multiply this plus 6x times 1 over 27 e to the 3x. Well, 6 over 27 is the same thing as 2 over 9. So 2, 9, and I have x e to the 3x. And then I do minus this product, 6 times 1 over 81. Well, the 3's will cancel out, and I'll be left with a 2 over 27. and that's going to be e to the 3x up there. And this, so that's the antiderivative, will be evaluated from 0 to 2. And so, I put in the 2, I get 8 e to the 6 over 3 minus 4 e to the 6 over 3 plus 4 e to the 6 over 9 minus 2 e to the 6 over 27 minus, and when I put in 0, this is 0 because of the x, this is 0 because of the x, this is 0 because of the x, and this e to the 0 is 1, so this is going to be a negative 2 over 27. And now I see across the board the least common denominator is 27. I could do some work here, but I'm going to just change everything to 27ths. So multiply this by 9 over 9, I get 72 e to the 6th over 27. Multiply this by 9 over 9, 36 e to the 6 over 27. Multiply this by 3 over 3, 12 e to the 6 over 27. This already is over 27. And this is already over 27. And so 72 minus 36 is 36, plus 12 is 48, minus 2 is 46. So I have 46 e to the 6th plus 2 all over 27. And now, one more thing, solving the equation. So if both u and dv are cyclic in their derivatives, for instance, e to the x, the derivative and antiderivative will always be e to the x. Derivative of sine is cosine, cosine is negative sine is negative cosine is sine. They cycle through. Then, not 10, then we will repeat until we cycle to the beginning. And this is the most annoying. There's a way to use the table with it, but it's awkward to get the correct thing out because we don't actually have anything cancel here. Let's look and see what happens. It'll probably take 2 slides to finish, so I left some space. I want to evaluate this. And notice sine, the derivative of sine is never going to go to 0. Derivative of a power of e is never going to go to 0. So I'll dive right in. I'll let u equal, sorry, not that one. LIPET, so e to the 5x. It doesn't really matter for this problem, but I'll do it this way. E to the 5x and dv equal sine of 2x dx. And that means that du is 5 e to the 5x dx, and v is going to be negative cosine of 2x over 2. And let me flip to a new, let me check my notes to make sure I don't mess anything up here. So this tells me that integral, and I'll change colors to help try to keep things somewhat clean, will equal uv, so that's going to be negative e to the 5x cosine 2x over 2 minus the integral of v du. So v times du will give me negative 5 e to the 5x cosine 2x all over 2 dx. And I can clean this up a little bit, so I see a negative negative, I see it's 5 halves, and so I will do that. And so I'll get a negative e to the 5x cosine 2x all over 2 plus 5/2 times the integral of e to the 5x cosine 2x dx. And I do the same thing. So let me change colors again. So I'll call this u2 and dv2. So same thing, I will let u2 equal e to the 5x. I will let dv2, actually let me do it over here so I've got more space. So u2 equals e to the 5x. dv2 equals cosine 2x dx. Okay, so we have u and dv. I'll try to write it a little bit neater because it's getting a little bit crazy. The derivative of this equals 5e to the 5x dx. The antiderivative of this is going to be positive sine 2x over 2. I go through the process again. So this all equals, I have this first term, negative e to the 5x cosine 2x all over 2 plus 5/2, and now we did u substitution on, not u substitution, integration by parts here, which means I have uv, which is going to be e to the 5x sine 2x all over 2 minus the integral of v du, so integral of, then let's see, we have 5e to the 5x sine of 2x all over 2 dx. And here's the wonderful little trick. I see e to the 5x sine 2x. I have sine 2x e to the 5x. It's the same thing. So let me bring this over to another slide and then finish off this problem. So I'll copy this over. And I'll write what the original problem was. The original problem was I wanted to find the antiderivative of sine of 2x e to the 5x dx. And I'll work this out, so I'm going to distribute this through. So integral of sine of 2x e to the 5x dx equals negative e to the 5x cosine 2x over 2 plus, I'll distribute this through, 5e to the 5x sine 2x over 4 by multiplying this by 5/2, and I'll bring the 5/2 out and multiply by 5/2 to get a minus 25 over 4 integral of sine of 2x e to the 5x dx. I'm just rewriting the order so we can clearly see, hopefully clearly see, that these are now the same. And you might be thinking, well, hold on, what do I do if they're the same? I just went in a big old loop and didn't get anywhere. But you did, because I can solve this like an equation. I will add 25/4 of this to both sides, so I have one of these integrals here, 25/4 of them here, and when I add, I will get 29 over 4 times this integral, is equal to this mess, so negative e to the 5x cosine 2x over 2. Sorry, this should have been a 4. I think I said 4, but I wrote 2. Plus 5e to the 5x sine 2x over 4. And in order to solve for this, I just divide both sides by 29 over 4, which is the same as multiplying by 4 over 29. And lo and behold, I get, let me put a C in here, I get the antiderivative of sine of 2x e to the 5x dx is equal to this times 4 over 29, while the 4 over 2 gives me a 2 in the numerator. And I'm still left with 29 in the denominator because 4 over 2 left me 2 over 1 there. And I multiply this by 4 over 29. The 4's cancel, so I just have 5 e to the 5x sine 2x over 29. Plus, and if I multiply some arbitrary constant, which I called C1, by 4 over 29, I get a different arbitrary constant, which I will call C. And the reason that I added the arbitrary constant at this point is, up until then, there were integrals on both sides, indefinite integrals, so they would both have the plus C. But once this moved over here, I have an indefinite integral, which of course could be off by any arbitrary constant, but I don't have an indefinite integral here, so I need to include that arbitrary constant. All right. Feel free to comment below with any questions, and I hope to be able to answer them.